Hello, this is Math 2270 coming to you from the College of DuPage during summer 2020, and this is the continuation of our discussion of higher order linear differential equations and such. A lot of definitions, huh? Let's change gears and solve a problem. This is the first second order differential equation that we're going to actually try to solve. So what we have is y double prime minus 9 times y is equal to 0. Well, you know what to do, so give it a go. Let's see how you did. I hope many of you came up with the idea that, well, two functions that could be solutions are y of t equal e to the 3t and y of t is equal to e to the minus 3t. And I just sort of arbitrarily took t. You could have used x's and it would have all been fine in the same kind of situation. But I'm going to say more and talk a little bit more systemically, but good for you if you came up with those as solutions. But what I'm going to say is we started out with y double prime minus 9y equals 0, but if we write that in operator theory, we would have that's the second derivative of y minus 9 times the function y is equal to 0. So it is a homogeneous equation. The coefficients here are constants. This is a 1 and that is a 9, so those are constants. But then what I'm going to observe is if you look at these solutions and you say, oh, let's consider this not as an operator equation but as a polynomial, and think of this as being m squared minus 9 is equal to 0. That could factor or use a quadratic formula or whatever, but we say the roots of that equation are m equal plus or minus 3. So you're looking at this and you're saying, I wonder if that's a coincidence or not. We were going to find that this really is not a coincidence. Moreover, if we take those two solutions that we came up with, e to the 3t and e to the minus 3t, and we compute the Wronskian. Now, to compute the Wronskian, what we're going to do is we're going to write the functions across here in this order. So this will be e to the 3t, this will be e to the minus 3t. And then underneath that, we're going to write the first derivative. So the first derivative of this with respect to t is going to be e to the 3t times 3 because of the chain rule. And similarly, when I take the first derivative of this one, it is going to be e to the minus 3t times a negative 3, again because of the chain rule. So you see now I've got the matrix inside the Wronskian. And now what I'm going to do is I'm going to compute the Wronskian. The Wronskian is going to be the determinant of this. So the determinant of a 2 by 2 matrix, if I have A, B, C, D, I'm going to multiply this way and then have a minus sign and go the other way, this times this, and look at the calculation and see what I have. Now, in this case, what happens is when I take e to the 3t times minus 3 e to the minus 3t, if you think about this, this is e to the 3t, that's e to the minus 3t. Those are going to cancel with each other, so when I take this element times this element, I get negative 3. Now, there is a minus that is going to exist here, but I get minus 3 here. And it's going to be minus when I take this one times this one. Again, what is going to happen is this is e to the minus 3t times e to the 3t. That's going to be 1. I get 3. So you see this is going to be minus 3 minus 3. And minus 3 minus 3 is minus 6. And minus 6 is never equal to 0. So you see, we know from our theorem that these two solutions of the homogeneous equation are linearly independent. And they're linearly independent on any interval because there's no t here. This is never going to be equal to 0. So you see, we had a linear second order differential equation, and we now found two linearly independent solutions. So try to tie this back to what we talked about before as you solve the following problem. So I want you to solve the initial value problem, y double prime minus 9y equals 0. And we have initial conditions, y at 0 equal 2 and y prime at 0 equals 1. Now, remember from the theory that we discussed, this does have a unique solution. So there is a solution and it is unique. Your challenge is to find it. You know what to do. Let's see how you did. Well, we know that, and this was the problem, I just put it here so we could look at it again. So we know from the theory that since these were linearly independent solution, any solution of this homogeneous linear equation, second order linear equation, is going to be a linear combination of those two. So it has to look like y equals c1 e to the minus 3t plus c2 e to the 3t. But now what I'm going to do is I'm going to use my initial conditions. So what I'm going to do is I'm going to say, well, when y is 0, I get 2. So if I put 0 in here, I have to set it equal to 2, and e to the 0 is going to be 1. So you see what I get for that is I get 2 is equal to c1 plus c2. Now, the next and last initial condition for this one says that y prime at 0 equals minus 1. So I have to take the derivative of this, and if I take the derivative of this, I'm going to get minus 3 c1 e to the minus 3t plus 3 c2 e to the 3t. But I'm going to put 0 in there, and I'm going to set it equal to minus 1. So I get this equation. So you see what I have now is 2 equations and 2 unknowns. Now, of course, to solve this problem, and I guarantee you there will be problems like this on tests in the future, you will need to solve this system of linear equations. And you should have done this while you were solving this, but you get that c1 has to be 7 over 6 and c2 has to be 5 over 6. So you see the unique solution to this initial value problem, second order initial value problem, is y of t equals 7 over 6 e to the minus 3t plus 5 over 6 e to the 3t. I think this was more fun than the definitions, but we're applying a lot of the theory that we talked about in order to do this. And this is a harbinger of many things to come. In closing for now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.